right, second speaker, Molly.
All right. So, I'm Molly. I work at Custom Made. I do their platform data stuff. And I'm going to talk about databases. So, so let's say you have a database of cats, right? And you need to tell the cats apart. So you have to number them somehow. So, you do this thing where it's like cat 1, cat 2, cat 3, cat 4, and that works great. And, if you're lucky enough, your database has some kind of sequence type, and it does that for you automatically. But when you start getting more data, then what happens is your data starts not fitting into one database. So you spread it out into multiple databases, you shard it. And so what happens now is that none of your databases know about the data in the other ones, so they don't necessarily know what the next ID is going to be. So it's kind of a problem. And you could do something like this, where all your databases talk to each other, but then, it's, yeah, they all have to wait on each other, which kind of defeats the purpose of you having to, spread them all out. So turns out you could do something else called a ticket server. And what that does is basically, you have a little service over here, and you say, hey, what should the next ID be? And it'll tell you. So it'll be like, cat number 57 is the next one, and you insert that in the database. But it still goes over the net or the network, and it's more infrastructure to build, and it's kind of a single point of failure. Turns out you can do some stuff where you can have 2 ticket servers, and you can have one of them give odd and one of them give even IDs, but it gets kind of complicated. So it turns out there's a simpler way to do this, and it's large random numbers. It's the mathematician's favorite. And so it turns out a pretty common way to generate random numbers is UUIDs, which is just as you can see, really, really huge random number. So because it's such a large space, chances are you won't get 2 IDs at the same time. And it's a standard, and there's great language support. It's all over the place. But turns out that, whoa, this doesn't fit in here. Database problem. Anyway, it turns out that the way that most databases store things, it goes through a lot of pains to make sure that your data is sorted nicely, so that when you're scanning through it, you're saying, give me the last 20 cats or whatever. It actually just has to go in one swoop on the hard drive. But if you fill it out with random numbers, then it turns out things are not in order, and it bounces all over the place, and it's way more reads, and also when you're writing, it's way slower. So it turns out UUIDs that are completely random are not a great way to do it. So actually, there's another thing you can do, which is version 1 UUIDs. And what that does is basically, it's the number of 100 nanosecond intervals since the adoption of the Gregorian. What? Well, anyway, what they actually do. So the idea here is that if you had a timestamp at the beginning, then your IDs would be time ordered, right? Because it would be, what was I going to say? Basically, because the time's there, your stuff would be sorted by time. But turns out they actually store it backwards. So here's the first part of the timestamp, and here's the second, and here's the third. And it's kind of ridiculous. And by the way, they're strings, and they're huge, and they don't fit in standard data types. So Twitter came up with this cool thing called Snowflake. And basically, they're doing kind of exactly what we want from UUID1, which is they're taking a timestamp, and they're sticking a unique machine ID, and then they're sticking a sequence number. And it's kind of like the ticket server. It's basically a separate service that you can query. And they're time ordered, and because they're random, you don't have to coordinate between servers, so nothing's blocking you from doing a lot of writes at the same time. And they're not huge. But this runs on JVM and Scala, and you have to set up Zookeeper, and you have to talk to a thrift service, and it's kind of a pain. And tons of infrastructure, and turns out our ops guy is actually doing like tons of stuff. So yeah, it turns out you can actually simplify this even further. And so here's what I came up with. It's basically kind of like Simpleflake. Kind of like Snowflake, where you have a timestamp at the beginning, but then you just stick a large random number at the end. And it's still time ordered, Still, you don't need any coordination. It's not huge, and it's pretty much all the characteristics we want. It's super simple, kind of dumb actually, and so it's really fast, and no delay, no single point of failure, no state to keep track of in anything, and it's pretty darn easy to use. And of course, wherever there's random numbers, there's chance of collisions, and I will talk about this later because it's probably going to take some time. But what you really need to know is that it's a pretty low chance, even at a pretty high rate of inserts, that you'll get a collision. And even if you were writing tons of stuff, well, comes a certain point where you better hire a DBA who will set up all that infrastructure for you. And when you do that, and when you decide to switch to Snowflake because it's very good, it's totally backwards compatible with it. And that's me. Yeah, and here's our engineering blog where we talk about this stuff, and it's awesome. So you guys should go check that out.
We have a question.
Oh. Yeah, okay.
So, if this is as good as Snowflake, why did Twitter make Snowflake more complex than this?
Because they need to be able to do way higher rate of insertions.
Okay.
So I could, for example, it would be faster. So so this is only 64 bits, right? So there's only 23 bits of random number at the end. So what's happening is basically, okay, so here, let's go to the collision chances thingamajig. So basically, because there's a timestamp, and the timestamp's every millisecond, you can only have so many IDs inserted in the same millisecond without you getting a collision, right? So you could make it larger, and then it'd be 128 bits, and it wastes a lot of space. So they wanted a small ID thingamajig that also was, guaranteed 100% to not collide. But for my use case, this actually, well, for the majority of people's use case, this actually works way better.
Yeah, it looks like a great solution for what you're looking for, but why are you so concerned in getting order in essentially what's the primary key? The purpose of the primary key is to be unique. If you need order, set up an index on a different field.
Because turns out a lot of databases will store, so MySQL, for example, does this thing called clustering, where basically your primary key is the order. And so you can, you could have like a, totally unique, so you could have a UUID, for example, right? But then there's other problems with that. For example, it's really huge. So what that happens is now you can have less records fitting in the same page, or you could have a secondary index, right? But what happens there is that the way it works is secondary indexes refer to the primary key. And if the primary key is huge, now your indexes are very huge. And you run into all these kind of problems of just having a really large blob index.
But you can set up a different field if you cluster index. You obviously don't cluster the table, but you have to have that in cluster. You can have your ID being unique and have something else in your cluster.
Right, but you still run into problems just stemming from you having a large primary key.
So here's what's clear to me. The part where you said at a terabyte a year you have to hire a DBA,
Yeah.
hire that guy.
Other
Yeah, I
question?
mean, it's a really good solution. I just didn't know.
Yeah.
Other questions?
So why do you use a random number? Why don't you just put a host ID and everything in there?
Because what happens is we bring up and bring down hosts all the time. And so now it's like one more thing that you have to keep track of.
How many hosts do you have?
Not very many, actually. But it's like another config option that you have to stick in there, and you have to take it out. And then what's happening is you embed the host ID in your key now. And so what happens if you want to, if you want to switch stuff over, then do you change the ID in the key and move everything over? Do you know what I mean?
The last bit of that,
But then that can change also, right?
But all you just confirm just being unique.
Hmm?
You just confirm that the things are unique, right? So you don't have to change that. Yeah, that's usually.
Well, I guess that's a fair point. Yeah, that could work.
question last.
It's similar to the question of concern of being about it being unique and using time as an ordering. So what are you have collisions in terms of time at 100 inserts per millisecond or second?
100 inserts per second, but you don't. That's like at 100 inserts per second. It's still like almost like this chance of collision is pretty much like less chances than you like winning the Powerball.
Right. Okay.
Right.
But still, what challenges are presented to you by chances of collision in terms of time versus chances of collision in terms of random number? Because if you're still, when you're searching through, if you're still eventually going to look for the unique ID, what gets taken away by the fact that there's a collision in terms of time?
Okay, let me try to. So, when I mean what I was trying to say was that it's not that necessarily that there's a. So what happens is if you were just doing completely random numbers, right? You have a really large key space and you fill it all up. But if you do it in terms of time, then what happens is over time your chance of collision doesn't necessarily increase because because every new millisecond is like a new key space, kind of. So is that what you were getting at, or why I went towards something like that?
No, it's more that, so you have a chance of collision.
Yeah.
So the chance of collision in the time part, and
Yes.
the chance of collision in the random number part.
Yes.
Now, right now you were demonstrating how much does it take to have a, yes, very low, but still a chance of collision in the time part.
Mm-hmm.
Now, what does that take away from the way your system works?
Oh, I
When
see.
there is a chance of collision in your time part.
It doesn't take away anything actually, because the two like the random part and the ID part are conjoined together. Like even you basically need a collision on both, right? Yeah. So that's the way it works. So basically, here's the chance of collision of the time part. Turns out this distribution is like a pretty decent way to model. If you have an average rate of insertion of X, what are the chances you'll get two things happen at the same time, and then you kind of have to multiply that with, the chance of the random stuff happening, and yeah.
Right. We're going to have to move on to the next speaker, but we'll have time to mingle and chat after. Okay?
Thank you.